today's live session. This is the week 6 live session for Market Basics to Advanced Technologies NPTEL course. I'm Gagan Meena and I'm a fourth year PhD student at Electrical Engineering Department of IIT Bombay. Let us start with today's session. We will be discussing a brief overview of week 6 and then we will discuss some questions and in between also discuss some topics related to those questions. And if you have any doubt, you can ask in between also and after the class as well. This is a reminder for the submission of assignments. The deadline for assignment 6th is March 5th and for 7th is March 12th. Please submit the assignments on time. And this is the link for the recordings of all the live sessions. And you can find it on the bottommost tab on the left hand side of the portal of the website. You can check the problem solving sessions tab. In that you will find the link for like live sessions as well as for the Google Drive for materials used while delivering these sessions. Okay, let us start with the overview of week 6. The week 6 following things were discussed. First, the adaptive smart grid protection was discussed, and then modeling of energy storage, modeling of DC microgrid components, and finally the operation of AC microgrids was also discussed. The first thing was why to go for adaptive protection system. What's the problem with the conventional protection system which we have been using since a long time? We have seen there are certain problems with the conventional protection system because of the convention. Now, because of the bidirectional power flow due to renewables, there is a problem, and the conventional power system will conventional protection system will fail in that case. It won't provide protection, and we will see what are the different issues in power system protection in the presence of these different types of IBRs. There are 4 challenges to power system protection, and let us discuss these first, and then we will go to the adaptive protection schemes. Okay, we'll discuss it here. So there are 4 challenges to the conventional power system protection. In the presence of DERs. First one is dynamics in the level of fault currents. What happens when the penetration of DR changes? It changes the fault current because the IBRs and the SB The synchronous based or inverter based DERs, they have a cap on the fault current which they can provide. There is a limit on these type of inverters. For inverter based DG, the limit is only 2 per unit. So based upon the type of integration of the distributed generation, network topology, and loading, the fault level keeps on changing. Yes. So when there is islanding, it will be operating in the grid connect in the islanded mode. That in that case, the direction of the power flow as well as the amount of fault current will change. While that will be different in case of grid connected mode. Let's say we have this main grid here, and here we have a circuit breaker, and here we have a load. We have a generator here and one generator here. This is G1, this is G2, and let's say there is a fault here. Now there are, for this fault F, contributions to this fault F will be due to these three. From this grid. One will be due to this G1. Let us call this as IG fault. This is IG1 fault and this is IG2 fault. There are total three currents, IG2 fault. So here fault current, total fault current is equals to IGF plus IGF1 plus IG2. Okay, so this is the grid connected mode. But now if we remove this, we change the mode of operation to islanded mode, then what will happen? The current provided, there will be no current from the grid side, and the total fault current will be equals to IG1F plus IG2F. And because these fault currents are limited, capped, this value will be different. Let us call this this is islanded and this is connected. So I fault islanded will be less than I fault connected. And if this falls below the trip setting, less than trip setting, then the relay fails to detect the fault. So this will be a problem in this case. Okay, this is the first problem. Second is, let me remove this one. So this is due to dynamics of fault current. Second one is the problem due to bidirectional fault. And this we already discussed. Conventional distribution system, we have only the overcurrent relay, which works only, which operates whenever the current goes above the trip setting. But it is oblivious to the direction of the fault current. The second is bidirectional power flow. This is the power flow or bidirectional fault current. Okay. Let us take the same system here. And let's say we have a one circuit breaker here, one circuit breaker here. This is CB1, this is CB2, and this is the load. And we have a generator here, G1. And the fault is here, F1. And there is a load here. Okay, now for this fault, Let's say we have one fault F1 and another fault is F2, which is here. Another fault F2. So what will happen for F1 fault? Contribution will be from G1 and contribution will also be from the main grid. Right? So this will be IG F1 and this is IG1F. And for the fault 2, the contribution will be from this one will be grid and this is from here. This is IG2, IGF2 and this is IG1F. Okay. GF2, small GF2. This is small GF1. Okay. Now what will happen in this case? This circuit breaker will see total fault current as net fault current as IGF2 minus IG I capital GF2 minus small GF2. And if this value is less than the trip setting, then it will not detect the fault current. It will reduce. The bidirectional power flow will, because it doesn't have a directional element, so relay fails to detect the fault. Although there is a fault, but it fails to detect. Okay. The third one is false tripping. Although there is no fault, but still there is a tripping. Relay tripping. False tripping. And last one will be the blinding of fault. So here we have relay R2 and here we have a relay R1, feeder 1. Here we have a generator G1 and there is a fault here in feeder 1. Okay, feeder 2 fault is there. Now for this fault, what will be the contribution to the fault? Contribution to this fault will be from this G1 and one will be from this main grid. Okay. So now what will happen? Fault is there in this feeder R2. But since if there is a fault current from this G1 to fault to this fault, if that fault current, because it is passing through R1 relay also, and if it goes above its setting, it will trip. Although the fault is in the different feeder. So there will be false tripping in this case. Similarly, now let us see the last one, which is the blinding of protection. Now let us move to the blinding of protection. Here what we are saying, here we have a relay and we have a generator G1 and there is a fault here as well. So for this fault, contribution will be from this generator as well as from the main grid. Okay, now what is happening? The utility grid contribution. So what we can see here, without DG, when DG was not there, and if there is a fault, so without DG, IGF is 0. This is IGF, and this is I capital GF. So IGF is 0, and if DG is present, with dg, then fault current is equals to Ig capital F plus Ig small f. And as DER penetration increases, what will happen? IGF will increase and IGF will reduce because total fault current remains same. Now, if this IGF is less than the relay setting, it goes below, then this circuit breaker here, this relay will not detect a fault. Although there is a fault, but it is blind to that fault because of reduced contribution to the fault current from the grid side. And this is happening because of the increased fault current contribution from the distributed generators. So these are the four issues, and all these issues are addressed by doing some changes in the protection system. First one is to make the direction to include the direction element in the with the overcurrent relay. So first, what we can do is with element, overcurrent protection element, add directional element. This will take care of the bidirectional fault current. This takes care of bidirectional fault current. Second is to make changes in the now because for overcurrent relay to act, there is a setting, right? Relay setting, the trip setting. But as we have seen that because the current, there is dynamics in the fault current, right? Due to network topology change in network topology, change in DER penetration. This is grid connected and islanded mode. And different types of DER. This changes the fault current, which leads to blinding of fault dynamics and fault current and false tripping. We want to avoid that. So as these things change, we still want the protection scheme, the directional overcurrent relay to work, irrespective of these changes. For that, we need to make the system adaptive, which can adapt to all these changes. For that, the adaptation are carried out with the plug setting multiplier is changed. So the IDMT characteristics, which is a function, which is a function of MPG, that we need to change depending upon the mode of operation. It should be able to change. And in this, for this adaptive protection, two schemes were discussed that we will see right now. Both are based upon the superimposed current. Last time we discussed, we saw that for the directional relay, The polarizing quantity was voltage. Because voltage phase doesn't change much during fault, and actuating or operating quantity is current. Is current. But here in superimposed current scheme, we are taking polarizing quantity as current and this actuating or operating quantity as a superimposed current. Superimposed positive sequence current. This is also positive sequence current. Okay, so here we are, let us see here why do we need adaptive protection? Because of bidirectional fault current. To address the issue, bidirectional fault current presence or absence of DER, different modes of operation of microgrid, difference in the level of fault current contribution because of types of DER which have different cap on their fault level contribution and change in the topology. So these are the different reasons why do we go for adaptive protection. First one is the bidirectional fault currents, and second is absence or presence of DERs, and then different modes of operation are microgrid like islanded mode, grid connected mode, or it's in transition phase from grid connected to islanded and vice versa. Difference in the level of fault current contribution, which depends on the type of DER. For inverter based, it is kept to 2 per unit, and for synchronous based, it is 5 per unit and more. And change in topology of the network. All these things will change the fault current levels and result in the different challenges which we have discussed in the last week for the dynamics in fault current, blinding of protection, and false tripping. All these things we want to avoid, and we want the relay settings to adapt itself when all different depending upon the mode of operation. To distinguish to address this bidirectional fault current issue, we add the directional element to the overcurrent element and do an AND operation. When both are active, then only the relay will trip. Otherwise, it won't trip. So for this adaptive protection scheme, two schemes were discussed here. Both were based upon the superimposed adaptive sequence current based. Positive sequence current was superimposed. Positive sequence current based. Means delta I1. I1 means positive sequence. Delta I1 F is equals to I1 F minus I1 free. Fault current minus the positive sequence free fault current. So this is a superimposed positive sequence current, which is used in this. And for backup relay, backup protection, it uses the negative sequence superimposed current. And depending upon the mode of operation, the plug setting is also changed. The time dial setting that is changed so that it can adapt to the mode of operation. And in the second technique, both here only positive, in first one only positive sequence, superimposed positive sequence current is used. In second one, both positive and negative sequence component are used. If one is unable to detect, let's say the relay fails to detect the fault due by this using this positive sequence current and negative sequence. So both are used here, or operation is here. Any one of them or both, if satisfy the condition, then the relay will trip. In addition to this, there was one more. So here negative sequence superimposed current is used for reliability, for increasing the reliability of the relay. And one more thing which was done here is considering the impact factor. Because one problem here which we have discussed is the difference in level of fault current contribution. This is this is addressed by directional element, and this is addressed by this by changing, adapting the time setting and plug setting multiplier depending upon the mode of operation, and this is addressed by the impact factor. The impact factor to avoid any miscoordination. So for DER, for inverter based DER, because the fault current is clamped at 2 per unit, and for synchronous based it is at 5 per unit. So this is increased to a higher level, and that this is reduced so that they are on an equal platform. There will not be, if gap is more between them, then their contribution differs, and that creates problem for the relay setting. But if we make them closer, then actual current will be same, but the relay will detect as different, and in that way we're able to overcome that challenge also, the type of DER. So the relay will not distinguish between the type of DERs, and based upon that the fault current will not change. Irrespective of the DER, the fault current will remain same. So almost same. So that is the purpose of using impact factor here. So these different challenges are overcome by using these different techniques. The first one is the adding the directional element to the overcurrent element. Second is to have adaptive settings. Adaptive settings for the adaptive relay settings depending upon the mode of operation. And third one is the impact factors. The next topic, which was, yes, what's the question?
Yeah, mode of operation means
So there are
in inverter mode of.
no, here we are referring to grid connected or islanded mode of operation.
Okay, okay.
Yes.
Thank you.
Because that will change the fault current, direction of fault current, and even the level of fault current also.
That means if it is connected in grid, then one setting will be used.
Yes, yes, correct. And for island mode, another different setting will be used.
Yes, sir.
Yes, so next topic was the modeling of energy storage. So here first thing which we discussed was the importance of energy storage. This importance of energy storage was now is being felt so much. Initially, when the renewable penetration was very small, then we didn't talk about energy storage. But now We are talking about even long duration energy storage, more than 8 hour duration. So can you tell what is the uh, maximum duration of lithium ion energy storage at present operational in around the world?
Around 49 hour.
Lithium ion battery.
49 hour?
No, 49 hours.
Yes, 49. No,
Where?
I think somewhere I read. That's why maybe
Actually,
wrong.
yeah, it would 49 hours would be for pumped hydro storage,
Okay.
not for lithium. Right now, most the maximum capacity is 4 hours, but there are tenders which have been passed for 6 hours and 8 hour in Australia. In Australia, in near future, maybe 1 or 2 years, within 1 or 2 years, you will see energy, the lithium ion battery storage up to 8 hours. Beyond that, there are then other technologies are available, like sodium sulfur is there, which is for 6 hour and 8 hours. 6 hours is operational. 8 hour is also this company provides 8 hour also. Right now, 8 hour, 6 hour is there in Dubai and China also. Then this more than this you will find using pumped hydro storage. We discussed in week 3 snowy 2.0 in Australia. It will be a very huge it will provide discharge duration up to 7 weeks. Sorry, 1 week, 7 days. So it's a very huge storage. 350 gigawatt hour is the energy capacity of that pumped hydro storage. As the renewable penetration increases in daytime, because solar intensity is quite high, so generation might be more than demand, and it generally happens. The peak demand in we have peak we have morning and evening peak. If you see the Indian demand curve on Usuko's site, you will find there are two peaks in our demand curve. Ideally, we want the load curve or demand curve to be flat so that the installed capacity is equals to the peak demand. But, but in practice, the installed capacity has to be much larger than the peak demand. Sorry. Here, install capacity will be equal to yes, peak demand and which is same as the average demand also. Because it is same peak demand is same throughout. But here the install capacity has to more than the peak demand, and which is much larger as compared to the average demand. For most of the time, that installed capacity above the average demand is not used. So it's an oversized system for meeting few hours of peak demand. We have a morning peak, then we have an evening peak. And solar is during this time. Solar is available during this time. So this here, this time. Here we'll be having solar generation. And this solar generation, if the penetration of solar is quite high, what will happen here? This demand curve will become like this. Net demand. So this black one is the net demand. This is net demand. And because this net demand is reduced, especially during these two periods, this is ramp down, and here we are having ramp up. Which generators will have to ramp up and ramp down?
Hydro is
Yeah, hydro will ramp up, ramp down, and hydro can ramp up and ramp down quickly. We have concern with these thermal generators. They have a ramping capability of around 1% per minute. 1% of their installed capacity per minute, which will be around 50, which is 15% of the installed capacity per time block. They cannot ramp up or ramp down more than that. And if we want ramp up, ramp down even more than that, then it is a then we have to curtail the excess solar generation which is there during the daytime. What we can do is, so here, if they are not able to ramp down more than what is required, then there will be curtailment of the solar generation. And if they are not able to ramp up here in the evening, during evening peak, then there will be load curtailment. If sufficient hydro is not available, or either you have to do load curtailment or purchase from market procurement at a high cost. Because during peak hours, the cost is even it reaches to the maximum the market ceiling price, which is rupees 10 per kilowatt hour per unit. So if we have storage here, then storage can store this excess solar generation during daytime and release it during the evening peak requirement and discharge it. We save on the cost. And if the storage has, even after meeting the demand, it is still there is some charge left in the storage, then it can even sell into the market and do energy arbitrage, earn, because market price is quite high during peak hours and it is charging during the solar time where the market price is least in the day. It will be around 2 rupees and here 10 rupees. So it will earn, the storage will earn 8 rupees per unit. If we subtract its operational cost, then still it will earn. Storage can earn. So this is called energy arbitrage. Buy cheap and sell at a higher price. So the same thing explained here. During RE excess or deficit, you can store the excess during RE excess time. And during deficit, the stored energy can be released. And in that way, we can also bring this peak down. This also peak will come down and this will also go up. So we are trying to flatten the load profile. The storage helps in bringing down this gap between installed capacity and the average demand. So this will bring down this will increase the plant load factor, which is average power divided by its maximum power. And that it is closely related to the efficiency of the plant also. If plant factor is high, it will operate at a higher efficiency. During islanded mode, yes, it can. An islanded when grid is not there, and then storage can. When grid is present, storage can charge, and during islanded mode, it can discharge to supply the demand to provide the energy balance in that case. Okay, next. And yes, we have already discussed this. Flatten the load curve and energy time shifting is it is change shifting the energy from one period to another. It was shifting this energy stored from excess solar energy stored during daytime to and releasing it during the evening peak. So this is shift of energy over temporal. It's temporal shift of energy. Yes, it can during islanded mode it can provide supply the demand meet the demand as well as regulate the voltage. And these are different types of energy storage. We have already discussed this in the week 3, mechanical, electrical, thermal, and electrochemical. Then these we discuss different battery terminologies, type of batteries, lithium ion, nickel metal hydride is there, sodium sulfur, vanadium redox flow batteries are also there. Metal air, metal ion batteries are also coming up. Batteries and then yes, their modeling. Their equivalent circuit was also discussed. And different factors affecting the battery performance. Next topic was the modeling of DC microgrid components. Why, when we already have the AC grid, why do we need to go for DC grid? Is there a benefit of having DC microgrid also? Yes. Any benefit of using DC microgrid over AC? Are we using DC right now anywhere in the grid, power grid? We have discussed this in week 1 introduction. Anyone? We have discussed about HVDC. We are using high voltage DC transmission, which becomes cost effective and the length of transmission. We have to transmit power over long distances. Then HVDC is more economical. And there are other benefits for HVDC. It's the right of ways. It requires it requirement for right of way reduces significantly. And then there are no skin effect, no eddy current losses, no corona loss. But now, why do we want to move, have DC in distribution system also? Because right now we have many loads are DC that we use. All the electronics loads, they internally they consume DC. They have battery, right? We use these mobile laptops, tabs, small portable devices. All of these devices, headphones, these earbuds, earpods, all these devices, they use battery and they internally depend on DC power. And we need to convert because our system is AC. we need to convert that AC into DC. So this AC DC conversion stage is there. But if we have directly DC supply, then this AC DC stage is not required. And this conversion efficiency will, and if we charging discharging, if we combine both, then it becomes AC DC AC. While charging AC to DC while discharging, again we'll find this in electric vehicles. Two-way loss. If we have DC fast charger, directly we can charge. So if we have a DC grid, then we can use a DC fast charger and charge the battery directly. No AC stage is required here. Right. Then loads are AC and even some sources are also AC. There's solar PV, which in India, solar PV is the dominant among all the renewables. But we have very huge solar potential. And then fuel cell, which will be coming up in future. So they generate DC power, and then we need to convert them, connect them to grid, and before that we need to convert the DC power into AC. And again, when because the loads are DC, then again we have to convert that AC into DC. So this DC AC DC conversion step and AC DC AC. So these stages we can avoid. These so overall efficiency increases. And then third element which we have already discussed is storage. Storage also requires DC power. It can directly work on DC power. If we have DC grid, then these stages can be avoided, and then there is no skin effect, no corona loss, no hysteresis eddy current loss. And control also becomes easy. No issue of harmonics. There is no harmonic issues because frequency is zero. To improved efficiency, no problem of reactive power frequency and harmonics, no synchronization issues, no hysteresis eddy current loss, and reduce congestion on transmission lines also. And then based upon different voltage levels, we have different DC. The HVDC we have already discussed. It's more than 500 kV, 500 kV and above, and it's used for synchronous tie. For we are using HVDC for long distance transmission as well as for interconnecting two two systems operating at different frequency. We all know that two systems which are interconnected, they not necessarily operate at same frequency. There might be some difference. So we have 5 regional grids. All are interconnected by these asynchronous ties. And that's how we are having a single frequency, single grid frequency. Then MVDC, medium voltage DC between 11, so it's 11 and 33 kV, and here also we can have control power transfer between two networks. And then LVDC, this we can use for our one house, and also in electric vehicles. This LVDC is used in electric vehicles, especially in the four-wheelers. And so this we can use for providing reliable power supply and for some islanded grid. Let's say some isolated or remote village, in that we can have a DC microgrid. Because we have solar rooftop there, we can have a storage there, devices we are using DC, then we can have a DC microgrid there. Because most everywhere we go, solar panels are there. Wind, we don't know, but the wind potential is not available everywhere. It will be mostly on the coastal areas or in the hilly areas. But in other places, solar potential is there. So we can have solar panel and use DC microgrid there. Then there are different DC microgrid topologies. We have single bus, one bus, and through that bus, all different types of loads and sources are connected. So if solar PV is connected, then it's DC-DC conversion, solar PV. Why DC-DC conversion is required in solar PV? And what will this be, a unidirectional or bidirectional converter?
Unidirectional.
Unidirectional and DC-DC. Why do we require DC-DC? Why can't we directly connect to the bus?
Voltage step up.
Yes, step up, step down. Yes, it will be. Voltage step up is required, and also control is also required because we want to have maximum power point tracking. For that also control is required, and that can be done incorporated in this DC-DC converter. And when we connect it to the AC system, there also we have two stages, DC, one grid side inverter and that generator side inverter. And generator side converter will have that MPPT algorithm, and grid side will have that inversion operation. Both can even be clubbed in one single stage also. The inverter will perform both inversion operation as well as MPPT. If this is solar PV, then if we have a wind, then we need to convert AC into DC. Fuel cell again DC DC. Storage DC DC. But this will be a bidirectional. What about fuel cell? Unidirectional or bidirectional?
Unidirectional.
So these different types of, yeah, so this was single bus, then we have multiple bus. Different bus can feed one single load also. And there are reconfigurable topology, and these are very reliable topologies because they have got redundancy in the topology. If one of the distribution line goes, still the entire system can the load can be met because it is a ring system. These lines are interconnected. These different lines. And here we have load as well as generation, load generation, load generation. Even if load is there, if this line goes, still all the loads can be met. Right? All the loads can be supplied. And if this line goes, and if there is a generation here and load, then it can meet. Still, some of the loads can be met. If both the line goes. If only one line goes, then always the entire load can be met. And maybe if system is designed in such a way that for any n-2 contingency, the generation will always be equal to demand, or generation will be more than demand. That way also system can be designed, but it will increase the cost of the overall system. The more reliable system we want, more we need to invest. The cost will increase in that case. Because the generation will have to be redundance more than what is required to meet that contingency. And then last we discuss different load models, constant current, constant power, and constant impedance load.
What
Okay.
is MTDC?
A multi-terminal DC.
Multi-term. Okay.
This is zonal based. Zonal is
Yeah. What is the difference between
the
zonal and
is
MTDC?
yes. In zonal, all three are different. Zonal is an extension of ring system. So just here we talked about ring, right? If we can create zones in this ring also, and these zones can operate independently. If there is contingency and these two line goes out, still the zone can work. The generation here will meet the demand here.
Okay, clear.
A multi-terminal is different than these two. It will have different paths, multiple paths for power transmission. Not a single. In ring system, you have if there is a one line is missing here. Okay, one line goes out. Then this is a generation here different generations can be possible. And these generators will supply the load. Okay. But in MTDC, there can be more than one path here. Parallel paths can be there. Redundant paths can be there. So this will add to redundant system. It will increase the redundancy in the system. Okay.
Okay, sir. Okay.
The zone is it's even more better than ring because one zone will can operate independently. Okay, then last one was the switch mode converters. Initially, earlier we were using this linear mode converters, but they were having very huge amount of losses, heating losses because they were using resistance. And then we switched to these thyristor based devices or diode based, SCR based devices, diode and thyristor based, MOSFET based high switching devices. So and these converters, these DC-DC converters, they can be of, there are two types. One is non-isolated and second one is isolated. The isolated will have an isolation between primary and secondary side, and this is possible by using transformers. So any fault on the primary side, it doesn't propagate to the second side and vice versa. But in non-isolated, this benefit is not there. So the most famous these three converters which we know, buck boost, they are non-isolated type. We are not using any kind of transformer here. Here we are using one switch, one diode, and one inductor. So using one switch, one diode, and one inductor, how many converters can we create? How many converters are possible? Yeah, can you tell? As you can think, it, it's a if you simply try to do this using permutation and combination in maths, then what will be the answer? If we do not use the physics of these switches, diode, and inductor, then what would be the answer? Anyone? 6 years, correct. If you use simple mathematics, then it will be 6. But uh, can we have, if we apply the physics also, then can we have all the 6 possible combinations? Are they feasible combinations? No. If there were more, then we would be studying all the 6 different types of converters. But we are studying only 3. You can try to arrange these switches and inductor, but you will find only 3 combinations possible. If we change the position of this diode inductor and the switch, then we will end up creating only these 3 combinations. Both buck, which is steps down the voltage. This V naught will be less than Vs here because this D is the duty cycle, which is between 0 and 1. So this V naught will be less than equals to Vs. And because we want V naught to be less than Vs, so D will always be less than 1. And it will be even more than 0. D is between 0 and 1. And for boost, it will V naught will be more than Vs. And in buck boost, both can be achieved. Okay. And if we want to, and one more, apart from isolation, yes, that is one disadvantage of these non-isolated converters is that they do not provide isolation. But another limitation is that the factor, this gain or what we can say transformation factor, which is this here Vs by V naught, here V naught by Vs. This ratio of output by input, it cannot be more than 4 in this non-isolated time. It will be maximum, it can go up to 4. But if we want to have more than that, then we need to go for transformers. In transformer, we can have the
That
ratio
means
can be large.
any configuration, buck boost or buck boost, maximum by 4.
Yes, maximum up to 4 times. If it input is 10 volts, then we can boost it maximum up to 40 volts. And beyond that, we will have to use transformer, the isolated versions, which are this choke and push-pull converters are there, choke converter. All those different isolated converters can be used. Okay. Yeah. So next part was the DC. Oh, sorry, AC microgrid. Operation and control of AC microgrid. And this was very important. And we will all these things we will come again in Here we are only introducing these topics are only introducing. In next weeks, the entire more detailed control, how actual control is there, decentralized, centralized, distributed control of these both AC, DC as well as AC DC hybrid microgrid. That will be seen in the next weeks, upcoming weeks. So here in AC, in both in AC, we will discuss DC, AC as well as AC DC hybrid microgrid. And both all these microgrids can operate in grid connected, islanded mode and the restoration mode or the transition mode. Okay. So in grid connected mode, they operate, DGs operate in PQ mode where the reference we derive from the grid. Let's say this is the main grid and this is the point where the DG is connected, distributed generation. So this is the point of common coupling. And this is used, the voltage and frequency at this PCC is used as the reference by the control which is used in the DG. And in this mode, the DG operate in PQ mode. It will provide constant P and active and reactive power to the, depending upon the reference signal requirement. Provide constant active and reactive power to the grid. And 1 hour is still doing that now again same problem. Okay, let me share the screen again. And I will share the PDF this time. Okay. Okay, I'm sharing the screen again. I hope it is visible.
Yes, sir. Possible.
We were here. So these are the different issues which we have already seen before. Different issues in islanding the microgrid. We have safety issue and damage to different equipments, and inverter malfunction is also possible. Yes. It's the pen. This detection techniques we have already seen: active, passive, hybrid, and communication. And yes, this part is the very important part. The control of distributed generators in AC microgrid. And here we can have two types of DGs: synchronous and inverter-based DGs. Synchronous, their control is similar to the thermal generators that we already have. And then the next is the inverter-based DGs, and there they operate in these two modes: islanded mode and grid connected mode. And in islanded mode, they can operate in these three modes. They can operate as grid feeding converters. Now the buzzword is grid farming converters. Right? Presently, most of the converters that we have are grid feeding. They are constantly supplying peak. They are operating in the PQ mode and deriving the reference from the point of connection. They operate as a ideal current source with a high impedance in parallel. Their parallel operation is also very easy. Multiple grid feeding converters can operate in parallel. Then next is grid farming converters, which now we are trying. So whatever research is going on is on grid farming converters, because once the grid is the microgrid is operating in the islanded mode. Now earlier, because we were having grid feeding converters, they have to have a reference voltage and frequency. When they are connected to the grid, they are able to take that reference from the point of connection. But now in islanded mode, that is not possible. So that control needs to be changed. They need a voltage and frequency control as the frequency reference, otherwise they won't work. Because that PLL is the building block in that converter, grid feeding converter. We will see in the next week, next week. Then that PLL requires that voltage and frequency reference. That voltage reference is used to lock onto the grid frequency. That is the work of PLL. And without that, grid feeding converter won't work. So we are trying to create grid farming converters, or converters which can switch from grid farming to grid feeding and vice versa. Let's say when uh, the microgrid is connected to the main grid, then all the converters can work in grid feeding mode. But as soon as there is an islanding operation, now there is no generator or grid which can provide the voltage reference. So one of the converters, one of the resources in the grid, in the microgrid, has to operate in grid farming mode, so that converter can provide a reference for all the other grid feeding converters. Or so that is one option. Either one of them has to take that role, or multiple DJs can take that role to provide a reference to all the remaining grid feeding converters. Now question is which one should be made as a reference? And if that, let's say we decided to have one particular converter as the grid farming converter, but due to some uh, outages, due to some problem in technical problem in that inverter is an outage, that plant is an outage, then, and if we have decided to keep that only that converter in grid farming, then entire microgrid will be, the entire load will be on curtailment, because the other generators won't be able to work because they are in grid feeding mode. Therefore, we need to have redundancy in that also, and it has to be adaptive. So that is also a challenge. How to make that, take that decision? Who will decide that? So microgrid controller, control center, that MGCC has to take that decision, but that algorithm needs to be robust to any kind of change in mode of operation or availability of DERs. All that needs to be taken into account. Because this grid farming converter will act like a voltage source, ideal voltage source with a small impedance in series, just as we have a generator, because it is working as a generator itself. And then third one is a grid supporting converter, and they are controlled current source. And same, they also have very high impedance in parallel. But here this is ideal current source, but this is a controlled current source. So they can provide this voltage and frequency regulation services. So they can support the main grid.
What is the difference between ideal current and controlled current?
Ideal current source, this the value, the current which is which this ideal current source is feeding, that is constant. It won't change. But control current source, that current that which is injected, it can be changed.
As like these just come.
So which one? These chatcom you say?
Yeah. As like
Yeah, yeah, that kind of yes role they can provide. So that current injected into the system, it can be changed, and it will depend upon the requirement. So this is for supporting for providing supporting functions. Let's say voltage is dropping at some point, at the point where this DG is connected. So it can support the grid in improving the voltage profile. Apart from supplying the active power. So it will also supply reactive power in that case. But that can also change depending upon the requirement of the system. Because we saw here that grid feeding mode, the here in grid connected mode means they generally operate in PQ control mode. But here it will not be in PQ control mode. It will change depending upon the requirement of the system. That's why it is supporting the grid. And this is feeding means it is simply just injecting whatever it is. The reference is set. Okay. Then yeah. So this was islanded mode. The next one is the grid connected mode. So here we don't have this grid farming mode because that is not required. Even if we have that will, that is, even without that also we can run. That is the case. Grid feeding is sufficient here because we are taking the reference from the point of common coupling.
then this all cases, this protection will be different. Adaptive protection will come into
Yes.
picture.
Yes. Yes.
That means DER is very challenging to protection.
Yes. That is true.
Any
DRS.
research scope in this field is available.
Yes. Yes. Research scope is quite. There is lot of scope and research scope and protection, especially in distribution system.
Where we have to start, because many things are here connected with feeding.
And most of the research right now has happening in this grid farming converters with respect to grid farming converters. Even now, IEEE has come up with standard for grid farming converters.
But grid forming is a new concept or existing?
So it's an existing concept, but it is evolving.
Evolving. Okay.
Yes,
That
it is a it people have been working on this concept for a long time, but it is still evolving. It's not yet means we are not completely it is not completely what we can say everything is not yet foolproof in this grid farming domain. Many challenges are still there which needs to be addressed.
okay. Thank you, sir. Then that field we can check the research gap.
Yes, yes, correct. We can work in that grid farming area. You can find many papers on many reports are also there on grid farming converter. You can start with that, do a literature survey, and then you can work, find gaps.
Thank you.
And this coordination is still a challenge. How to this control of this and the switching from transitioning from grid feeding to grid farming mode when there is a change in mode of operation of microgrid from grid connected to islanded. How to make this transition very smooth? That is still an open area of research. Algorithms can still be improved. A lot of scope is there in that. Okay.
Okay, sir. Thank you.
Okay. Let us move to the next slide. Yeah, so this last topic was this microgrid ancillary services. And this also we have discussed. And so we have discussed this in context of the entire grid ancillary services, but same ancillary services are also there, can also be provided by here we are talking about microgrid as an element which can provide different types of ancillary services to the main grid. In normal operation, it can provide frequency control support to the main grid. It can help in reducing the grid losses because in microgrid we are having distributed generation, and if we are able to supply most of the demand using that distributed generation, then we need not transfer this consume power from the transmission line. We need not import power from the main grid. And that will reduce the losses because transmission line the power has to travel such a long distance. I square R losses increases. So if we meet the requirement locally, then we can reduce the losses, grid losses. Then power quality improvement, microgrid can help in that. And then voltage control support and congestion management is all these things are possible. In islanded mode, black start is one of the services which it can provide because once let's say one region entire when this 2012 blackout was there, once blackout is there, after that the system needs to be again restart, and we cannot bring the entire system back in one go. We need to start in small patches. And because microgrid are already we have created small pockets, zones, and these zones can, if they have sufficient generation, or they can start with the critical loads for that generation is sufficient in microgrid, and then slowly all these zones can be connected, and then once all the zones are connected, then the thermal generators, they can be brought up, and slowly this entire restoration process can be made very fast using these microgrids. Or if storage is also there, storage will be a part of it, so that will also help. And in islanded mode also they can provide voltage and frequency support. Okay, let us start with questions. What is the value of coordination time interval maintained between primary and backup relays? What's the answer? So this is as per what was maintained in the case study discussed in the lecture. The uh, 0.3. I think it was 0.5. 0.3. Okay. 0.3 is correct. Good. Next question. This is based upon the superimposed current technique which was used. So here it is saying there are two buses, bus 1, bus 2. And from bus 1 to bus 2, the load at bus 2 is drawing a current of 250 amperes before the fault in the normal condition. But when the fault is there, the current increases to 1600 amperes. So what is the superimposed current at bus 1? Very easy question. What will be the answer? Yes, correct. 1350. C is the correct option. 1600 superimposed current means the fault current minus the pre-fault current. Fault current is 1600 minus 250 will be 1350. And so this is the same thing which we were discussing. The superimposed current based adaptive protection. So here this is the in direction element we discussed last week that polarizing quantity is the voltage and the actuating quantity is current. But here we are not working, we are only working with currents. And here the polarizing quantity is the positive sequence pre-fault current. And the actuating quantity is the superimposed current, positive sequence current. So we have to compare this superimposed positive sequence current with respect to the pre-fault current. The angle difference, so this is delta I1 F1 is the superimposed positive sequence current, and which is equals to the fault current, positive sequence fault current minus pre-fault positive sequence current. For both the faults are F1 and F2. An angle we can find by taking difference of angle between the superimposed current and pre-fault current. So this is for two different direction of current. If I pre is this and this is IF1, IF2, and if we take the difference of I fault minus I pre, then we will get this delta I1, the superimposed current. I fault minus I pre means this I pre will vector will become negative, and then we have to take the resultant of this I pre and IF1. Let me try to share that uh, PowerPoint again so that I can write on the PPT. I hope it will work. Yes. Okay. Good. Yeah. So this I pre will this because we want negative of this. Let me take a different color. Okay, so this is minus I1 3. And now we have to take the resultant of this positive sequence fault current and the pre-fault current. So this will be the resultant. Similarly, for this I3 and IF2, we have to calculate. This will be the resultant, delta IF2. Now we have to take the angle. We need to calculate the angle. So this angle, difference between superimposed fault current and I1, the pre-fault current. Because this superimposed fault current is leading. So this difference will be positive. Right? So this will be positive. And this will be negative because here pre-fault current is leading. This one is ahead. Default current is ahead of this superimposed fault current. So this will be negative and this will be positive. And based upon this, we can know whether the fault is behind the relay or in front of the relay. And for the reverse current, this I1 pre will be here. And then again, we need to take negative of that I1 pre. So we need to take the resultant of these two, pre-fault current and I1 pre. It will be here. This will be delta I1 F1. Similarly, we need to take the resultant of these two. And it will be here. And actual I1 pre is this one. This is negative of I1 pre. This is I1 pre. Now I1 pre is leading. Earlier it was lagging. So it will change, reverse. The forward will become reverse and reverse will become forward in this case. Because current direction has changed. But for this, different relay will act. Because these relays are overcurrent, directional overcurrent relays. Now this will make the things clear. It is a very good question. And it was discussed in class, but not as a it's how this came up. It was directly tabulated in the lectures, so I have made it as a question. Here we have to identify the backup relay for fault F1 in the grid connected mode, in the islanded mode. First, we will do it assuming that it's a conventional system, conventional protection system. So this is the first case of conventional protection system.
Fault in F1.
For fault in yes, for
F1
fault F yes, for fault F1. Now, if this is a conventional system, that means here we don't have any kind of distributed generation, and the current will flow only in one direction. And it's a radial system, and current is only unidirectional, right?
That
So
is
here,
only from grid only.
yes, only from grid up to this load, and from here to here. So in this case, three relays will become redundant. Which are those three relays?
Which fault? For F1 only, R1 only. Fault F1.
For all these three fault for this entire system, if we consider
Yeah, R3 is the main relay. R2 and R1 is a backup relays for fault F2.
for fault F1,
For fault F1 only R1 only will act.
yes, correct. So if we consider these all these relays as directional overcurrent relay, then this R1 will work for this direction of fault current. R2 is set to work for this direction, R3 for this current, R4 for this, R5 and R6. Okay. Because here this is a conventional system, so direction element is not required. So this R2,
it is a radial feeder only.
yes, radial and only unidirectional current is there, so no need.
No need direction.
So R2, R4, R6 become redundant. We don't need them. Okay. It is so this we have only R1, R3, and R5. Now fault is in F1. So for fault F1, R1 is the primary relay, right?
Yes.
And there is no backup relay for R1 here.
Yes.
It's the only relay which will work for this fault. But if fault is here in F2, for F2, fault in feeder 2, R3 is primary. Because fault current is like this. And R3 will act. And the relay which sees current in the same direction and which is behind this R3 will act as a backup relay. So which relay will act as a backup relay for R3?
R1.
R1. And for fault F3, primary relay is R5.
R5 and the backup is R1.
Correct.
Backup is R1.
Yes. So this primary and backup. This is backup. So for F1, we have only R1. There is no backup. For F2, R3 and backup is R1. For F3, R5 and backup is R1. Okay, so this is just clear. This is for the conventional protection system, protection scheme. Now we have the DGs in place. Okay, one is here, one is here, and this is a grid connected mode. Okay, first we will do the grid connected mode. Now here we need all the 6 relays, two for each feeder to take care of the bidirectional current flow.
Yes.
So if there is a fault here in F1, in feeder 1, fault F1 is there, then how many currents? One current is this. Let's say, let us first mark the direction of currents here. So R1 will operate for this, R2 for this, R3, R4, R5 and R6. Okay. These are the intended direction. Now for fault F1, the current will be contributed by grid. Current will be contributed by this first DER and by second DER also. Right? So now
Yes.
which one is which relays are primary relays for fault F1? So how many relays are primary relay?
2 relays, R1 and R2.
Yes, so 2 relays are there because we have current in both the direction. For same fault current is one current is in this direction, which R1 can take care of, and 2 currents are in this direction, which R2 can take care. So R1 and R2 become the primary relay for fault F1, primary and backup. So here we have R1 and R2. Okay. So for R1, what is the backup relay for R1? So if we see behind R1, there is
no relay.
There is no relay. There is no backup relay for R1. But for R2, which one is the backup relay? Which all relay are seeing the same current in the same direction as R2?
R4 and R6.
Yes. So we have R4 and R6, which are behind R2. So if R2 is unable to clear the fault, then after a few seconds, R4 or R6 will trip. Okay. What about fault 2? If we have fault 2, then fault 2 current from grid, current from DG1 and current from DG2. So what are the primary relays for fault F2?
R4 and R3.
R3 and R4. And uh, what are the backup relays for R4?
We can say R1 and R6.
No, for R4.
R4 nothing.
R4 no backup. Right? And R3 you are saying R1.
R1 and R6 also.
Yes, correct. R6. So R1 and R6. Good. Now only remaining is this F3. One current is from this second DER, one is from this first DER, and one is from the main grid. So what are the primary relays for fault F3?
R6 and R5.
R6 and R5. And backup relay, there is no backup relay for R6.
Yes.
For R5,
R5, R1 and R4.
Yes.
Like F2.
R1 and R4 are the backup relays. Okay. Is this clear? Okay, good. Now we'll move to the islanded mode of operation. Now here, fault F1. But for fault F1, what is the prime? Which all relays are the primary relay?
In islanded mode, one DR will be cut, or
one DR will be?
In islanded mode also this DR will be there.
Which one, R1?
No. I am asking about the DER supply will be
Yes,
there.
yes, DR are there. Both DRs are present in islanded mode. Only the main grid is not there.
The main grid is not there.
Yes, but they are operating.
Yes.
They will be operating in, one of them will be operating in grid farming mode.
That will be the reference voltage.
Yes, that will set the reference voltage, and the other one will be following it. So here R1 is not required, right, for F1 fault.
Yes, R1 will not require.
Because there is no, but it is still required because whenever grid connection is there, it is required. But for islanded mode, R1 will not participate in protection. So here we have F1 fault, F2 fault, F3 fault, and primary and backup. So for F1 fault, primary is
R2
only, and backup is
R4 and R6.
Yes, R4 and R6. For fault F2, which one is the primary relay?
R4 only.
R4 only. Oh, only R4? We have
R6 and R.
No, primary relay.
R3 also.
R3 and R4, right?
Yes, R3 and R4.
And backup relay for R4?
R6. R4 nothing.
R4 no backup. And for R3?
R3, R6.
Yes, correct. Now the last fault. For F3, one fault current is this, another fault current is this. So what are the primary relays for F3 fault?
R6, R6 and R5.
Backup for R6?
Nothing.
There is no backup for R6. For R5?
R4.
Yes, because R4 is seeing the current in the same direction. R4 is the backup. Okay, is this clear?
Yes, yes.
Correct. Good. So only R1 is not required here. Otherwise, all the other relays are required, either primary or backup. Okay. So for F1 in grid connected mode, what was the question? Backup relays. So R4 and R6 are the backup relays. Fiber optic is an example of which type of network? It's easy question based upon previous weeks. Which one? Wide area? Yes, C, correct. Wide area network. Compressed air storage is a form of electrical, mechanical, electrochemical, or thermal. Which one?
Mechanical. BB.
B, mechanical, correct. So in mechanical, we have pump storage, compressed air storage, we have flywheel, and we have this gravity-based storage also. Gravity storage is also. Have you heard of this gravity storage? I think we had discussed this in week 3. It uses potential energy. It will lift a block for charging and then release it. And that potential energy is converted into kinetic energy. And that is used to rotate the turbine and generate electricity. So it's a mechanical. What is what are the benefits of energy storage? First, it improves the battery storage, improves the reliability to utility consumers, reduces system losses and improves efficiency, reduce peak demand, provide ancillary services. All of the above. Yes,
All of the above.
all of the above, correct. Now we have to select the equivalent model of a supercapacitor. Now you have to see each and every element very carefully and then decide which one is the correct option. It's a supercapacitor. So few options are already, you can remove certain options, right? You're saying B option. B option is not correct. The 3 options we can directly, or at least one option we can directly remove out of this. Out of these 3, one we can directly remove.
Yeah, C we can remove.
Why C?
Because
Yeah, correct. Even we can remove
C.
2 options. There is no capacitor, C is gone. And also one more option we can remove directly. Yeah. Why? No, A cannot be removed. Is there is A and D we have to think. But B we can remove because there can be, every wire has the inductor. So R can be there. in series with L. But this L alone coming in parallel with R.
R is required along with L.
So this is not correct. It's a supercapacitor, so inductor, at least it will not come in the parallel. Even if it is there, then R should also be there.
Okay. Some along with the impedance, along with the inductance, some resistance is required
Yes.
in parallel with the capacitor.
Yes.
Okay.
So this option is correct. Because here in series with capacitor, resistor will also be there. Always. It will always be there. So here we have C and R in series and R in parallel. No other option is fitting. This is not correct because there is no resistor here. This cannot be there. This is outrightly rejected. Okay, clear?
Yes, that means along with the capacitor, some resistance will be there along with
Yes,
the
it is
inductor
there.
or capacitor.
Yes, it is there because we cannot have idle capacitor and idle resistor. Inductors are not there.
Oh, okay. That concept we can use
Yes,
here.
we can use this.
That means if it is along with the inductor or capacitor, the resistance shall be there in the
Yes,
equivalent diagram.
yes. Okay. So A is correct answer. This also we have discussed. Which of the following statement is in isolated mode is correct? All DGs operate in PQ mode. All DGs operate in VF mode. Some DGs operate in PQ and some in VF. None of the above.
C.
Which one?
C.
C. Yes, C is correct. With an islanded mode, there is no reference generator. So some of the DGs have to take the role of this providing reference, and others can operate in PQ. So C is correct. This also we have discussed. Ring DC microgrid is an example for single bus, multi-bus, reconfigurable topology, none of the above.
B.
Yes, correct. Reconfigurable. Which of the following statement with respect to grid feeding converter is correct? They operate independently in islanded mode. They cannot operate in parallel with other grid feeding converters. They can participate in the control of microgrid AC voltage and frequency. Which one is correct? And none of the above.
C. C, sir.
C option.
C.
C. Yes, C.
C.
Yes, C is correct. Because they cannot operate independently. Without reference, they cannot operate. And they cannot operate in parallel with other grid feeding converters. So that is B is also not correct. The converters used for battery, PV, ultra capacitor, and PMSG wind system in a DC microgrid are respectively are. So we have to select which one, bidirectional or unidirectional, which one is required for each of these. So what's the correct answer? Battery, PV, ultra capacitor, and PMSG wind system.
A.
Battery bidirectional, PV unidirectional, ultra capacitor bidirectional, and EMS unidirectional. Correct. Because ultra capacitor is also a storage, ultra or super capacitor. Last moment it has stuck. I'll have to again open. I will share the PDF. Why this happens? This is done. This is done. This is done. Grid feeding converters are connected to the grid in which which combination to inject power to an energized utility system. Grid feeding. These are grid feeding converters. We have discussed. In parallel with low impedance, with high impedance, or in series. Which one is correct? I hope it's visible, right?
Yeah, visible, sir.
Which one? Which one is correct?
Confusion.
Confusion.
Yes.
Why? Confusion between which option? So here in last question we already said no, this question. You said this is not correct. They cannot operate in parallel with other grid feeding. That means they can operate in parallel. Now two options are already gone. C and D. You have to choose between A and B. Now between A and B, which one will be there? B or A? So B will be correct, right? In parallel, the impedance has to be small. No, it has to be high. In series, the impedance has to be small so that there is no drop, very negligible drop across that. Similarly, in parallel, if impedance is high, drop across that will be negligible. Okay. Which of these is not the microgrid ancillary service during grid connected mode? This is also very easy. Frequency control, congestion management, power quality improvement, or black start. What's the correct option? A, B, C, or D? No answer. Which one? D is correct, right? Black start is there when microgrid is islanded. Okay, this was the last question. Do you have any doubts? Are you saying something I can't hear? No doubts? Okay, then we will meet next Monday then. Thank you for joining the session.